Hey guys, continuing on here, we're going to do 20 and 27. In this one, I'm going to tell you 20 and 27 both are really, really good problems, and they are kind of my favorite ones. And so that should be a clue that these will show up at some point. So let's take a look at problem 20 first. I have it written down right here. And in this, here's what the issue is to start. You can see that my variables are stuck up in the exponent. And as long as they're in the exponent and I don't have the same base, I have no idea how to turn this into a same base problem where I can just equate the exponents. And so because of that, somehow I have to get those powers out of the exponent and down into what I call the main line of the problem. There's only one thing that I know of that allows me to bring powers down, and that's this rule right here. And so whenever you log something and you have anything to a power, that power is allowed to pull down in front and multiply it. Notice that it's the whole power times the whole log. And so when I do this, I need to bring down, so I'm going to log both sides, and just like before, I would use log or ln or log base 2 or something like that. In this, I can pick any log I want because this rule actually holds for any base. And so it'll hold for base e, the ln or natural log. It'll hold for base 10. And since these don't have any real good bases, I'm just going to use the one that's easiest to write, and that's ln. So I'm going to say ln of 2 to the x plus 1 equals ln of 5 to the 2x minus 1. Once I have that, those powers now do both come down. And so this is exactly why I had planned to do this problem this way. So we have x plus 1 and then ln 2 equals 2x minus 1 ln 5. A big thing, and this is partly why this is one of my more favorite problems, is that notice I put parentheses around both of these. And that's because the rule itself specifically says it has to be the whole power times the whole log. I pointed that out before. And if I didn't have the parentheses in there, it would only be 1 times the log, and the x wouldn't be times it. And so it does really need to be there. Once we have this, I'm gonna stop for a second because a lot of times students see this and they get intimidated by this. And so here's what I want to show you in the center column right over here. What if I had something like this, like x plus 2 times 3 equals, let's say, 3x minus 1 times 4. All right, so one little piece here. Notice I have an x plus 2 times, and that's a number, and then 3x minus 1 times, that's a number. Over here, I've got x plus 1. ln 2 is a number. And ln 5 is also just a number. And so, over here, that's just a number and that's just a number, just like 3 and 4. But they don't look as nice as 3 and 4. And so I think that's the only reason that students sometimes get intimidated in this problem, is just due to the fact that the way that we write those numbers are unusual compared to the way that you're accustomed to writing them. But here's the thing. If we were going to solve this problem, we would distribute the 3 and get 3x plus 3 times 2 is 6. And on the other side, when we distribute, 4 times 3x is 12x minus 4 times 1 is 4. Now what I would do, and I'm going to do this quick here, I'm going to move the 3 x's to this side, and I'm going to move the 4 to this side. So if I add 4 over to the 6, I get 10. If I subtract 3 x's from 12 x's, I get 9 x's. And then if I divide, I get x is 10 ninths. Okay, watch how I did that, and watch how this is done exactly the same way. So what did I do first over here? I distributed. So what am I going to do here? I'm going to distribute and say x ln2 plus ln2. So that's 1 times ln2. And that's an x. And then over here, when I distribute the ln5, I get 2x ln5 minus ln5. Okay, now we're here. So this is exactly the same as that line. What did I do when I was here? I said, let's move numbers to one side and let's move variables to the other side. Well, I've got variables here and I've got numbers here. So I'm going to move the ln5 over to this side. Reason is because then it'll be a plus. And if I moved this over, I would have a minus and another minus, and I don't like that. And so on that other side, I already have an ln2, and I'm going to add an ln5. So that ln5 coming to the other side becomes plus ln5. And when I do that, those cancel out. ln2 and ln5 don't go together right now. They're not like terms, but we do have something in the future that will help us with that. On the other side, then, I had a 2x ln5 already right there, and this I'm going to move over to this side. So it's a plus on that side, so it's a minus over on this side, minus x ln2. All right. What did I do then over here? Well, here's what really happened, and this is where it seemingly looks different. But if here I went 6 plus 4, and here I went 12x minus 3x, what I could have done is pulled an x out, and I would wind up with that 12 minus 3, and then 12 minus 3 is 9. So I'm going to do the same thing here. Notice I have an x and an x in both of those. So I can pull out an x. So we have ln2 plus ln5 equals x. If I pull it out, I'm going to have 2 ln5 and then minus just an ln2. Now all I did to finish was divide by whatever was attached to the x. Well, now this is what's attached to the x. So I'm going to divide by 2 ln5 minus ln2. Divide by 2 ln5 minus ln2. Those will cancel, and I get the answer. X is ln2 plus ln5 over 2 ln5 minus ln2. Okay, couple things that I want to show you now with that answer. And this is what it is. So if I was in here and I said parentheses ln2 plus ln5 parentheses divided by 2 ln5, I need a parentheses there, 2 ln5 minus ln2 the answer is 0.9116518. If we went in here and we said 2 raised to the x plus, x plus 1, and we said 5 to the 2x minus 1, you can see they do cross somewhere, and where they cross is at 0.9117, and if we went back here to our calculator, it does round to 0.9117, and so that is the answer. That is checking it on a graph. All I've done is I've graphed each side of the equation. So in here, I graphed this side as y equals and graphed that side as y equals. And if those are going to be equal, well, then the two y's would have to be equal. And on the graph, they are equal right there. And that happens when x is 0.912. So the other thing that I want to show you is this. We have a lot of rules that allow us to do things. I'm going to write them down here because you should be comfortable and accustomed to them. We had a rule that said ln, or actually it said log base b of m times n is log base b of m plus log base b. Sorry about that. I got cut off for a second. So where I was saying we have a rule that was log base b of m times n was log b of m plus log b of n. What that means is, more specifically, that ln of m times n is equal to ln of m plus ln of n. Now, we're going to use it this way going backwards. And so we have two things added together, and I want to make them into just a product inside. So here I have them added together. So I could make that ln of 2 times 5 or ln of 10. So if I put that in, that's an ln 10 on top. And then on the bottom, we already talked about this rule that says you can bring powers down, but then that should mean that we could take numbers out front and stick them back up. And so that 2, I'm going to move up there, so that should be ln of 5 squared. But 5 squared is 25, and so that would be 25, and then minus ln 2. But now I've got subtraction, and remember that ln of m over n is ln of m minus ln of n. So anytime that you have subtraction like this, we can replace it with a division inside the log. And so I'm going to take that. I'm going to rewrite the whole thing. So we have ln 10. In the bottom, it was ln 25 minus ln 2. That's ln of 25 halves. And so this answer right here and this answer are exactly the same. But this one is the most simplified. Notice that we do have division of logs, but that's not subtraction. It has to be log of, and division has to be inside. I never said anything about log base b of m over log base c of n. That's not anything at all. And so, in that, if I still, I still have that up there. If I said ln 10 divided by ln 25 halves, notice it's exactly the same number there. So since that is the same, that shows you in a calculator that they are equivalent, and they are equivalent through nothing more than the properties of logarithms, that's multiplication, that's actually an exponent, and then that is actually division within the log right there. So that is how you do that problem. It is a little bit complex. It's a little bit more involved than this, but in reality, there is no difference than there being a 3 and a 4 out there to distribute, and there being an ln 2 and an ln 5. That's the truth. Okay, one last one on this, and then I'll move on to the next set of problems, starting at with whatever the next section is. So our next one's 27, and I have it right here. And in 27, there's something really neat that happens with this. So this is actually a hidden quadratic. And why it is the following. Because e to the x squared is e to the x times 2. So a power to a power we multiply. And that's e to the 2x. So this e to the 2x right here is actually e to the x squared. And so, if I erase this, this is really e to the x squared minus e to the x minus 6 equals 0. And we've talked about this earlier in the term. We talked about things called hidden quadratics. And with a hidden quadratic, you could do this. I don't like this, but if I said, let's let w equal e to the x, well, then this would be w squared minus w minus 6 equals 0. That I could then factor and say, okay, well, then that should be w minus 3 and w plus 2. So then I guess w equals 3 or w equals negative 2. And because of that, I know that w was e to the x, and so e to the x equals 3, or e to the x equals negative 2. Now, I have these two secondary equations to solve, because I still have x trapped up in that exponent. And so, because it's trapped up there, the only way I have to get exponents down is by taking a logarithm of both sides. So, if I log the left side, I get the ln of e to the x equals the ln of 3. And remember, the inverse properties of logs, ln of e to the x equals x. It's like the ln and the e cancel each other out. So here we get x equals ln 3. And in a previous video, I already explained this, but the graph of e to the x is always positive. The range is 0 to infinity. And so there's no way that that'll ever hit negative 2. You can see that in this by taking a look at e to the x. And here you can clearly see it never shows up below the x-axis right there. So it's never negative, and so I already know that there's no solution to that. But if I did ln both sides, those cancel and I get x is ln of negative 2. Also in a previous video, we said you can't log negatives because a log graph looks like that, and the domain is 0 to infinity. And so you can't plug any negatives into a log. If I went into the calculator and said, what's the ln of negative 2? Remember, it says not a real number. And so, since it's not a real number, this one I don't have to worry about. But if I didn't notice at first that that can't be negative, the calculator would tell me when I check my answers. And so that doesn't work. Now I'm going to show you how you can check this in a calculator. So I'm going to graph this equation right here. If I graph it, we will have, and I can go here, we're going to say e to the 2x, and then minus e to the x minus 6. And we wanted to know, where does e to the 2x minus x, or e to the x minus 6 equal 0? Well, y equals 0 is the x-axis. And since it's the x-axis, then I'm wondering, where does the graph cross this line right here? And we have an answer of ln 3, which in a calculator, the ln of 3 is 1.099. Basically, it's 1.0986, but we'll say 1.099 in there. And so, look at what we have. If I come over here, there's the 1.099, and that's the only spot where that graph crosses that axis. As a matter of fact, if I put in there x equals, and the exact answer is the ln of 3, you can see when I zoom in, they do cross right there at that point. And that point is exactly that answer right there. So that's how you do these two problems, but all of them in here are the same thing. You would divide and then take a log, or you're going to add that to the other side and divide by a 5 and then take a log. You're going to subtract 2, divide by negative 6, and then log. in, where was it? In problem 21, that's another one just like 27. And 26 is one just like problem 20. And those are the only two that are like that. All the other ones, if you move the 7 over, divide by 4, you can log both sides and get an answer. So, anyway, that should be enough to get you through this set. Hang in there and keep plugging along.